All right, now I've got my note-taking program properly set up, and I've got my blank made for next time. So it's now 5:30. I'll ask one more time. Anybody have any questions for me? This could be old homework questions from any of the previous chapters, chapter three including. It could be, syllabus questions, proctoring questions, online test questions, face-to-face test questions, anything. All right. Well, I guess we'll get started. Last time when we met, we actually had worked out, I gave you basically what would be an introduction to vector algebra. So I introduced the idea of what a vector was. I used as a metaphor for Johnny, really loud. So as a metaphor for addition of vectors, I use the idea of sort of each step you take creates dang it, I forgot the name of the vector now. A displacement vector. Specifically, it is a displacement vector that starts where your feet were standing initially, and then after the step, that would be where the head of the vector is. And then you could take another step, and that would be another vector. But what I did was just treat it as, we're going to break your walk up into several little short, straight jaunts. And in that case, that was an idea that worked. So what we ended up getting was a bunch of vectors that were, of some length, and we just basically imagine one vector from your front porch to some area in front of your house, then another vector walking parallel to your road, crossing your road, and so on and so forth. And what we discovered was if you just put a series of vectors in head to tail configuration, and oddly enough, the order doesn't matter at all. I mean, the order matters in the sense that if you do it in one order, you might run into a tree. But if you do it in another order, you actually might be able to successfully walk, and another, order might actually end up getting you in a pit. But still, if you were able to complete all the individual vector steps in any order, then the resultant, the sum of all those vectors, A equal, or let's say R or S, R for resultant or S for sum vector, is equal to A plus B plus C plus D, or it's also equal to D plus E plus A plus X plus Y plus Z plus C. Doesn't matter the order at all. Again, if you put them in the order that you walk, then it makes a little bit more sense and follows the actual path you took. But the main thing is you then draw a vector from the tail of the first vector, no matter which vector you chose as the first vector, to the tail of the last, or excuse me, to the head of the last vector, no matter which one you chose to be the last vector as well. And then that vector that goes from the head of the first to the tail of the last is the sum of all the vectors that you added. Using that, we were able to make some sense of what it means to multiply a vector by a scalar, what it means to add two vectors, all sorts of stuff like that. I taught you how to add them in a component form. And I didn't get to teach you yet about the unit vectors that we use, and that's the more modern slash robust way of dealing with vectors. So I've got to introduce you to that real quick. So let's get that started with started on, and then I'll just jump right into projectile motion, solving some very specific projectile problems. But for starters, we're going to start with just a straight projectile. That's sort of the generic case. So we'll do that as well. Let me start by asking again, when is the face-to-face test? Okay, so the first face-to-face test, someone asked, it's already available. It came available this Monday morning, and you have until the 9th to get it finished. So you guys have to get a proctor between now and then to get that done. Check whatever dates, of course, I put for you on the syllabus, but if I remember correctly, it's till the 9th, and you have until then to get that done. You also have until then to get online test one done. You also have until June 16th to get online test two done, but I did suggest that you at least try online test one and online test two before you even took face-to-face test one, specifically because face-to-face test one covers chapters one and two, which is what online test one is, and it covers about the first half of chapter three. So it only covers basically vector addition and some of the most normal fundamental questions of projectile motion, just the concepts, not so much solving a projectile motion problem. So that's what that first test's on. And like I said, you have to have it proctored and completed, like I said, by June 9th. 11:59 p.m. if I remember correctly. But you can check within your Canvas for your page, look in the modules, look in the face-to-face test, and you'll see the deadline on that. As I warned you in the syllabus, if something comes up, you're unable to find a time at one of the testing facilities that our campuses offer, or if you can't find some other way of doing it, then just let me know. And obviously, you don't want to let me know on the 9th. You want to let me know before the 9th and say, hey, I'm not going to be able to make it get the test finished by the 9th. Can I have an extension? And I'll probably just grant you one. Okay. The main thing is you really need to try to get it done, and the next time I might not be quite as willing to move dates around and stuff like that. But please just try to keep up with the pace. I completely understand. I'll work with you if something comes up to help you and extend any deadlines that need to be extended. Uh, I understand the summer is kind of a brutal thing to cover. What normally covered in 16 weeks, we cover in 10 weeks, or what's normally been covered for a little while in 15 weeks. We're now covering it in 10 weeks. So I get that that's hard. Uh,
Hey, good question, Professor.
yeah, I see Eli asked the question. Is that you? Or, oh, no, you're David. Go ahead, David, and I'll answer Eli's next, or
I
Ellie's.
was gonna say I had two short questions. So
Okay.
I wanted to know how we're supposed to complete lab number three. We're having software issues.
Yeah, I just got an email, or I just saw the email from one of your fellow students, actually from one of the 002B or 1B sections, and said that the software that you were supposed to download isn't able to be downloaded now. So I'm
Yep.
obviously going to have to push that back if it stopped working. But it literally was working just, at the end of last, or excuse me, I should say at the end of last semester was when it was working. So I don't know what's going on. I'll see if I can find another one, but obviously you guys will have an extension of at least 1 week. So don't
Okay.
worry about that. And I'm always going to do that for you guys. If anything ever comes
I
wrong,
appreciate that.
it's obviously I'm going to take the heat for that. So yeah, I'll fix that. Someone else,
Okay, and then
go ahead. What's the other
hold
question?
on. And then my proctor had sent you a text regarding
I think that's the one from
Sunday.
Dave.
Yeah,
Is
he was asking me if he should message you, and I was like, just because we're not in the States right now, I wanted to make sure that you just reach out as early as possible, even though it's
right.
about a week in advance. So he
Was
should have texted you.
was it
Huh?
a chief?
Yes.
Yeah, I got that. I noticed that one today. I'll be replying to him today after class. So
Okay. Yes, yes, Professor. Thank
done
you.
everything right. Everything you've done is fine. So there's nothing wrong with anything you've done. I'll
Uh,
the application. You'll see it's a really short application. He literally just says, "Yeah, I'll do it," and then I send him the password and that sort of thing. Do you have a webcam?
not yet.
Okay.
Just because I don't know how I would do a webcam in this exact situation.
Yeah.
But
Are you
I
actually
can
on the
say,
ship
well,
where you're allowed to
yeah,
film it?
kind of, yeah. That's why I'm kind of that's why I was like, okay, well, I'd have to use my proctor obviously because I don't have a webcam available. But
Yeah.
I mean, you and my proctor will. I mean, you'll tell my proctor whatever we need, and then he'll obviously tell me what to do, and we'll figure it out.
Yeah, yeah, that's not a problem. It's mainly one of the ways that I can allow more people to proctor is by making
Yep.
sure you guys have webcams, and then I can sort of see if anything's fishy going on, know
Yeah.
who it is. So that's the ideal scenario. If you don't have a webcam, that's okay. I just have to make a separate version of the test for you. If you do have a
Understandable.
webcam or you have access to one, please get one, and it'll just make life a lot easier for the whole process. Well,
Okay.
from the proctoring and the grader standpoint, not necessarily from the student standpoint. So
Yeah, well, I understand. I mean, if my proctor tells me that I can have a webcam and whatever you guys talk about, because my ESO doesn't really talk to me about that stuff. I only really talk to them when I need to sign my tuition assistance or when I need to get a test proctor. So they're pretty like distant, like they're very professional, but it's
sure.
not somebody that I talk to on a regular basis. It's only when I'm doing my degree plan, updates, all those types of things. So,
And
hi,
that's
Professor.
better for proctors anyways. I don't necessarily want them being friends. I mean, I don't want them being enemies either, but yeah, it's good.
Yeah, no, exactly. It's more of like a
Professional.
definitely a supervisor to like subordinate relationship for sure.
All right.
So
Just don't
you
let them
you guys,
down for anything. Don't let them use a power play against you.
nah, I think it'll be fine. I haven't had an issue.
Yeah.
All right, thank you, Professor.
Doubt too many people, abuse their power that way, but that's always a concern
Yeah,
when I have a boss with a underling. But yeah, I'd
I
like to
understand.
send him back something, and if y'all can get one, that's great. If you can't, that's okay too.
Okay, all right.
Eli or Ellie. By the way, I never got the final understanding of whether that's Eli or Ellie, so I apologize. Know I'm doing it 50% incorrect every time. So the process to get a test proctored in person at TCC, if you happen to come tomorrow, if you could come tomorrow, for instance, I could proctor you myself. That would start around 12:45. You could start as probably as early as 12:10, 12:15, something like that. And then you run till like 3 o'clock if necessary. But generally, you only need about 45 minutes to an hour to get the first test done. If you want to do it at a testing center, they require an appointment, and the latest I heard, they were wanting an appointment 48 hours in advance. I've already sent everything so that you guys can be tested. So they've already got the stuff from me. You just have to make an appointment and find one that fits in your schedule. They do have nights, but it's weird. It's like Virginia Beach campus will have one night a week, and then Chesapeake campus will have a different night, and then Portsmouth campus will have a different night, and then Norfolk will have a different night. So you got to look for that. There are other proctoring services as well, though. For instance, teachers and guidance counselors at schools as well as at universities and colleges. I allow you to use those. I do not specifically, read the syllabus, but I specifically don't want you using friends and family. But if someone like that is available to you that works within a school system, they can send me a text message, let me know their name, their position, what school they're at, and use their school email. Then I can approve it by sending them a little application, which tells them specifically what they have to do. They have to say that they're, basically they have to swear that they're willing to do that. And then later I'll send them the actual code so that they can get in. The ideal scenario, as I mentioned in the text messages and emails, excuse me, well, I did do text messages too, but I mean emails that I sent you guys. The ideal scenario is that everyone's using a webcam so that you can use Respondus Lockdown Browser and Respondus Monitor, even with a proctor. Now, if you're doing it at a testing center, you don't need that. So there will automatically be a version made where they don't have to use the Respondus Lockdown Browser if you go to the testing center. But if you're going to a non-testing center, meaning you're getting a friend, or again, I did say specifically not friends and family, but if you get someone that that works in the school system, then ideally I want that to be recorded with the actual monitor. And I normally even require you guys to have an additional mirror so that I can see your screen, your hands, and the keyboard at all times. So, like sometimes I've asked people to like file in a Zoom meeting, use their phone, the camera, and they'll stick it over here to the side so that it's actually filming them. And from the camera on Zoom, I can see the screen, the keyboard, your hands, your waist, or your lap, that sort of stuff. That's really the standard that needs to be adopted when we're doing proctoring tests because I have a lot of experience catching a lot of people cheating. Okay. Any more questions about that?
Quick question.
Mhm.
Do we get like a cheat sheet or anything on our test?
Yes, if you look in our modules in the Canvas for your course, under My Documents and links, you'll see something called Allowed Equation Sheet, and then you'll see front cover two, stuff like that. Those are all the things that will be at the bottom of your test when you take the test.
Oh, okay.
Okay. If you wish to bring a hard copy of the actual equation sheet,
Hmm.
I usually send the proctor a electronic version that they can print out themselves. But you could also print one out yourself, but then the proctor has to actually take a picture of it, all the sheets that you use front and back, and send them to me before you go into the test so that I know exactly what was on your equation sheet. And whether you added things to it, that sort of stuff. So it's really just better to let them print it or to just use the version that's in the test.
Okay. And then if I like go to like the testing center, I don't have to bring my own laptop, right? Or do I have to come with
You
my
do
own stuff?
not. No, you do
Okay.
not have to. But if you come to one of my labs to do it, it would help
Hmm.
if you brought your own laptop.
Okay. Thank you.
And also, if you do it in my lab, we don't use the camera, but we do use Respondus Lockdown Browser.
Okay, cool beans.
No problem. Someone asked, could they make their own equation sheet? You can make them for your own practice, but no, I just won't have the time to actually go through everybody's independently made equation sheets. Specifically, the equations that I put on the equation sheets are the ones that I allow you to use. I don't allow you to use any ones that aren't on it. So that's another big reason. There are specific equations that the author comes up with from, doing derivations or solving problems, and then students will grab them and just apply them. My hypothesis, or my way of interpreting at least what the authors mean, is if they numbered an equation, then they probably meant for one, them to be able to refer to it later, but two, they might have also said this is an equation that the student might want to be able to use at any point later. So if one's not numbered like they are in the text with some parentheses, that's definitely not one of the equations that's going to make it in the equation sheet, and I don't want them in there. Okay. Anybody? Oh, yes. Far as the mirror goes, if you wanted to actually take this proctored at home, I will allow that, but you are going to have a mirror, you are going to have a webcam, and you are going to have to run Respondus Lockdown Browser and Respondus Monitor. And I will need, like I said, a mirror of some sort so that we can use, if your webcam, for instance, is attached to your monitor, then we'd need to put the mirror like somewhere back here where it allows me to see the screen and your hands, and then you can't be stuffing your hands where I can't see it from the mirror. So that's one thing. If you actually have a webcam that you can move around, then the best case scenario would be take the webcam and lay it right over here to the right so that it shows me your screen, your keyboard, your hand, your desktop, and I can see all of that. So if you're willing to make sure you have a big enough mirror to do that and make sure you have a webcam, then I will absolutely allow everyone to take their test via proctoring like that. I'm not sure about the final. I probably still would. I just haven't made that decision yet regarding the final. So hopefully that would help a lot of you people. The reason why I stopped doing that some time ago is because the hassle of the mirror. And there's still ways where people can try to cheat. And if I catch that, then that means y'all are going to have a more difficult life again. So hopefully I won't catch anybody doing that. And just take your good grade or take your bad grade and run. It says in the Pearson lab, in the in-person lab, Dr. Johnson mentioned something about him possibly being able to proctor for us the first test during lab time. That is the ideal scenario, but some time ago we had proctors, or we had adjuncts teaching labs, and they didn't show up for us to do tests or final exams. So if they'll actually test you in the lab setting, that's perfect. I want you to do that. That would be the best case scenario. And all you need then is a Respondus Lockdown Browser. So yeah, if Dr. Johnson's doing that, that's awesome. I'd love them to do it for those 3 face-to-face tests. I'd love them to do it for the final too. But like I said, some time ago, we ran into a problem where adjuncts didn't want to cover, or didn't. Well, I'll just say, being that we value our adjuncts so much, we know we don't pay them sufficiently, and we don't feel right in forcing more work upon them. So we just decided to stop doing that to some extent, or at least I did. So if he's doing that, that's great. I'll go with it, but find out also if he can do it with the final. If he can, then that solves a lot of problems for everybody. I will check. I did get an email from him once already, and I already replied to that, but I'll check. He might have sent me another one since then. So I have a movable webcam. Do I need to express permission to do that? No, no, that's fine. Basically, when you use the webcam with the Respondus monitor, I immediately see the whole video of what you're doing. So I will know specifically what you're doing. So the goal is, like I said, take a movable webcam, stick it off to your right or your left, somewhere where I can consistently see during the entire testing procedure and testing time. I can see at least part of your monitor as well as your keyboard and your desktop. And I don't want to find you ever, looking down at something where I can't see. If I find that that's going on during the testing, I'm probably going to stop it right then, make you have to take a retest. Okay, so just don't do that. All right. Keep all the stuff on the top page. Keep your desk area kind of clear so I can see your hands and all that stuff. And then keep everything right here on the desktop in front of your monitor or your laptop computer so that I can see a little bit of your monitor. But most importantly, I want to be able to see what your hands are doing and what your keyboard's doing and your head and all that good stuff. So, any other questions? And yeah, you don't have to let me know anything special if you're doing that. I'll just assume that you're going to have the test done on time. And if come the 9th, if I look around and the test's not done, I'm going to start sending emails to find out what happened. And it might just be that you did it already, but you did it at home, and I'll check the video and you'll be fine. So that's for all of my online students. That's my NO2B and my my O01B as well. So any other questions? I took a lot more time than I expected, but I'm glad that y'all are asking me. So if your lab teacher will proctor us, do we still need a movable camera? Absolutely do not know. If your lab teacher is going to proctor you, your lab teacher will be watching you. He can monitor whether or not you have an equation sheet that's allowed, and it'll have Respondus Lockdown Browser. By the way, I had the Respondus Lockdown Browser installed on all the computers in the labs, JC21 and JC26, as well as JC28. And you should be able to just go in there and double click on the lockdown browser to start it. But if you have your own computer, by all means, bring that, because we only have 12 computers and we normally have 24 students. So the more people that have their own computer, the less time we have to waste waiting for one person to finish before another person can start. Anything else? That was a lot of words. I'm having some difficulty. Some of my students are concerned that they don't understand what all has to be done. They feel like, I guess, that they should be able to just read the syllabus and know exactly what's happening every minute of every day of the class to some extent. And I'm not trying to, I'm not trying to make an absurd argument or anything like that. I'm not trying to do that. I'm just saying that they said that I need to express to you that I don't think it's possible, nor do I think that's a goal, to write a syllabus that completely explains everything to you. So that you can't, that you don't need to ask any questions. A lot of times you probably could, but I don't think that's a goal. I really want my students interacting with me to some extent. So if you're having problems with that, make sure you contact me. Make sure you follow the instructions on the syllabus, so that if you email me and you don't get a response within 1 business day as defined in the syllabus, then send me a text message so that I can respond to it properly. So anything else before we begin? Thank you for asking all those questions. I know we took up a lot of time. That doesn't upset me. It's fine. Good news is the second half of chapter 3 is really easy to finish in a day. That's why I split it over 2 days. Ideally, I would have liked to start into chapter 4. I don't think I'm going to be able to do that, but that's okay. I just wanted to get the 3 knocked out. Also notice that I did push, because you're doing your homeworks for chapter 3 this week. It's normal that your homework be due Sunday of this week, or for you guys, since y'all meet on Tuesdays, it'd be due Monday of this week. So, or excuse me, Monday of next week. So I did move those dates, which were like the 23rd or something before, and I moved them back to the 9th or 10th or 8th or 9th or something like that. However, when I was just going over what you had to do, meaning online test 1, online test 2, face-to-face test 1, I'm thinking I'm not gonna push the due date for chapter 3 back to as far back as it was, like the week of or like June 20th or something. I might push it back to like the 15th or 16th or somewhere around there, just to make it a little easier on you. But just remember, if you don't have at least the first half of chapter 3 homework done before you take the first face-to-face test, you're not necessarily well prepared. But if you took the practice test enough times for chapter, or for online test 1, the chapter 1 and 2 practice test, if you took that enough times and you took a bunch of chapter 3 practice quizzes, you'd be good to go. Okay, so even if you don't finish that homework in time, that'll be fine. So I will change that right after class tonight. I think that addresses one student's complaint or question from my 0015 1B class. But anyways, I literally just changed yours just before class, but I got thinking I think I am going to move it back a little bit. But don't think of that as the norm. Remember, if you're doing chapter 4 on a given week, you should expect chapter 4 homework to be due by the Sunday, or in your case, the Monday of the following week. So just keep that in mind. That's the way it's supposed to be done. And I'm trying to get y'all in the groove of doing that on time every week. So I'm really hesitant to change it, but I think it would be best if I change it. So I will. Okay. All right. Now I'm going to go ahead and share my screen with you from my iPad. So let me do that. I'm also going to turn on the chat so that I can see if y'all type anything. Remember, you know, y'all are paying me the $7 million a year I get for being a teacher. So you have the right to stop me and question me, and I want you to interact with me and stop me and question me. So by all means, please do that. Anytime you have something that you don't understand, or something that I explain, or some algebra or calculus that I do too fast, I want you to stop me and ask me, because I'm pretty sure that if you have the problem, then there's probably in this class probably another 10, 15 people that have the same problem. So please take me up on that. Any questions on anything before we get started? All right. So what I'm going to first off do is I'm going to show you the last of uh, last class meeting. So if you remember correctly, when I added those vectors together, the four vectors together, I got a resultant. And the way I got the resultant is I ended up breaking my vectors A, B, C, and D down into X and Y components. And the way I did that was by using this little drawing with the really bold, thick red and green arrows. The green arrows are supposed to represent arrows that are in the positive, or excuse me, in the negative coordinate direction, and the red ones are in the positive coordinate directions. So all the red ones should go right and up, and all the green ones should go left and down. And you see that's what they do. Then, if you'll notice, for instance, with vector A, which is this guy right here, you can see that I took the time to write out what sine was for this particular angle and what cosine was for this particular angle. And then I used that to solve for the X and Y components. And remember, I specifically force us to choose the signs of the components. I highly recommend you do that. I mean, you don't want to waste time thinking exactly what this angle is. Like if you converted it to a counterclockwise measure of angle from the positive x-axis, and then you just plug that into cosine consistently, it would give you the x component and the sine. I don't want you doing that. Okay. For starters, it's really easy to make careless mistakes when you're converting those angles. And also, it's way more physical for you to think about which direction it's pointing, and then orient yourself so that you can figure out which direction is the positive direction, which direction is the negative direction. So in this case, I just chose a particular angle. I could have chose the 38.87 degrees or 36.87 degree angle here if I wanted to. That would have been fine as well, but I would have had different sines and cosines. I chose this angle, and sine being opposite over hypotenuse gave me opposite, which is a sub y, this guy, over hypotenuse, which is the magnitude, which was 10 newtons, this guy. Similarly, cosine is adjacent over hypotenuse. This is adjacent, this is hypotenuse. So the adjacent you can see is AX, and the hypotenuse is 10. And I, by seeing it moving from the tail to the head, I had to move right and up. That means both the X component and the Y component are positive. The X component is positive because I had to move to the right. The Y component is positive because I had to move up. When you get over here, the Y component is positive because I had to move up, but the X component is negative because I had to move left. But that's the way we do it. And then we just find usually the smallest angle between the vector and the nearest coordinate axis. So I could have used the 45-degree between this y-axis and this vector, or I could have used the 45-degree between this vector and the x-axis, which is the negative x-axis. All of those are fair game. Same thing here. I could have used the 30 degrees that this is below the negative x-axis, or I could have used the 60 degrees that it is to the right or to the left of the negative y-axis. All of those are completely fair to do. I always choose an angle between 0 and 90, and then I assign my signs as I'm going along, and then I make sure I consistently check the signs to make sure they all work out. So I've got a plus and a plus here, and then I'll look and I see, okay, the x is plus and the y is plus. Then at the y, I see I've got a plus for a y component, that checks, and then I got a negative for an x component, that checks. Over here, I got a negative x and a negative y, and sure enough, the x component being negative checks, and the y component being negative checks as well. And then finally, this one, I have a negative y component and a positive x component, and sure enough, the positive x component is there, and the negative y component is there as well. Looking back and remembering, positive 6, positive 8, that checks. Negative 5, positive 5, that checks. Negative 6.93, negative 4.00, that checks, or 4.00. And then D is positive 8, negative 6, positive 8, negative 6. So each of those check. Now I put them in a table form and I add the x components up to get a new x component that gave me positive 2.07 newtons. And now I add the y components up and that gave me a positive plus 3.00 newtons for the y component. Now I have the components, and had I taught you about the unit vectors, then I would have a answer right now. And that's the key part. The whole reason I went back to review this is to show you this key part. So we've got R has an X component that's 2.07 newtons positive, and it has a Y component that's 3.00 newtons positive as well. So at this point, you might not realize it, but the R vector that we were just talking about, there's your R vector. Okay, that's the resultant, that's the sum. We determined, which again, I'll go over this, I'll finish rehashing exactly how I got those numbers in a second. But in this case, what we're trying to do is realize that positive 2.07 newtons in the x direction and positive 3.00 newtons in the y direction gives us a vector R that equals positive 2.07 newtons, and then I'll put a little parenthesis. You don't always have to do this, but it often makes it a lot easier to understand and see. And what we would do is we'd say there exists a x component vector, meaning a vector that is only lying along the x-axis. So it's either a positive x direction or in the negative x direction. But the main thing is it's only in those directions. And that vector is basically a certain magnitude, 2.07 newtons. And all I have to do to make it a vector is take that 2.07 newtons and multiply it by a vector that is 1 unit long and points in the positive x direction. Because if it points in the positive x direction and the x component is positive, then the positive 2.07 multiplied by the unit vector pointing in a positive direction just gives you a vector that points in the positive x direction. So that vector happens to be called I hat. So it's just like XYZ is part of the alphabet, IJK is part of the alphabet as well. And we let I represent X, we let J represent Y, and we let K represent Z. So we would write this 2.07 newtons times I hat, and that represents the X component of the vector, which is in fact a vector. Okay, because I put the I hat on it, that makes it a vector. Now I'm going to say plus positive 3.00 newtons. And now this one points in the positive J direction or in the positive Y direction. And the unit vector we use for the y direction is the j hat vector. So notice the little hat that we see on top of the vectors. Those hats indicate unit vectors. Okay, and a unit vector means its length is exactly 1 unit. So if you took I hat's magnitude, that's one way of writing the magnitude of a vector, is you just write the vector inside of absolute value bars. Another way is sometimes you'll write double absolute value bars like that. And then another way is you would just write the vector with no vector symbol above it. All of those are reasonable. And in this case, the answer is +1. Notice it's not +1 meter. It's not +1 Newton. It's just +1. Okay, so that's key to understand. The same thing is true about the j hat vector. And for obvious reasons, we don't like using the j hat vector as just the j, just like we did with the I. We don't really like doing that. So I'm not going to in this particular case, but the magnitude of j is is +1. And then similarly, k hat, its magnitude is also +1. And the main thing to understand is that the I hat points in the positive x direction, the j hat points in the positive y direction, and the k hat points in the positive z direction. And now that we're talking about 3 dimensions, you need to always make sure your coordinate system is right-handed. So let me draw you really quickly a right-handed coordinate system with the unit vectors on it. So what I'm going to do is I'm first off going to draw an x-axis, which I represent as coming out of the screen like this. That's my x unit vector, or excuse me, that's my x axis. Now I'm going to draw my y axis, which is on the page, but pointing to the right. So there's the y axis. And now, if you use your right hand rule, you stick your index finger in the direction of the positive x, which is out of the page. You stick your middle finger in the direction of positive y, which is to the right. Then your right thumb points in the direction of the z direction, which is upward. So that's the key to the right-handed coordinate system, is using that right hand rule there. So this is the z-axis. Now I can write the unit vector in the x direction is this little vector I hat. The unit vector in the y direction is this little vector j hat. And the unit vector in the z direction is the unit vector k hat. So that's what they are. Any questions on that? Now, just to refresh ourselves further, we were talking about this. So once we found the 2.07 newtons positive being the x component and the 3.00 newtons positive being the y component, all I had to do was draw an x and y coordinate system, as I did here. And then since the 2.07 is the x component and it's positive, then I drew it parallel to the x-axis and pointing to the right. Similarly, at the head of the x component, I drew the tail of the y component, and then I drew it upward because it too is positive. And that allowed me to see two sides of a triangle, or two legs of a triangle that is a right triangle. You can see this angle right here is going to be 90 degrees. And this angle right here is the angle from standard position that we recognize from trig. So if I were actually able to find that angle phi, then that angle could just be stated as the vector points in the at phi direction. So that's what that's what I did. I basically took the fact that these two were legs of a right triangle, and I used Pythagorean theorem to find out what the magnitude was the 2.07 newtons squared, and then the 3.00 newtons squared. When you do this part, remember you've got to trace out the actual digits from the 2.07 and the 3.00. Those are both 3 sig figs. But when you square 2.07, that's 3 sig figs times 3 sig figs. So you're only supposed to get 3 sig figs as an answer. But when we square it, it becomes 2.07 squared is 4.2849. But remember, you only had 3 sig figs, so that means you know the 2.07 squared to the hundredths place. You're going to have to call this 2.07 squared, which I'm going to write on this page right here. The 2.07 squared is equal to 4.2849 newtons squared, but the 4 and the 9 are not sig figs because, again, you only had 3 sig figs. When you square the 3, that one's a little easier because you know it's 9, but that also tells you that you can put more digits after the 9.00, but they will not be significant. So now that you see this, you see you're going to add a 9.00 and a 4.28. So you're going to get 13.28, but 13.28 is only significant to the 8 in the tenths place. So that gives you 3 sig figs. When you take the square root of that, it gives you 3.645. And in fact, the 5 in that is not significant. So technically I have to put that 4 right there. And what we would say is that the magnitude of this vector is 3.64. And now to find the angle, all I have to do is take the inverse tangent. Remember, tangent through our alley, our TOA, is tangent equals opposite over adjacent. That's opposite, which would be 3, over adjacent, which would be 2.07. If I take the inverse tangent of 3 over 2.07, I get 55.39. But those were 3 sig figs each, so I shouldn't get more than 3 sig figs out. I'm going to call that 55.39, but I underline the 9 because clearly that is not a significant figure. So finally, I can say that the vector is R, whose magnitude is 3.64 newtons at the standard angle of 55.9 degrees. So that's how we went through all that. And this answer, 3.645, that is exactly equivalent to this answer, which is also right. So we could write 3.645 newtons at 55.39 degrees, and that's exactly the same as the answer I put above with the 2.07 newtons I hat and the 3.00 newtons J hat. Any questions on that addition stuff? Okay. All right, so now that I've finished that, that's just a lot easier way to add vectors. So now instead of having to find components, if someone says, hey, vector A is 3 I hat plus 4 J hat, and vector B is negative 7 I hat plus 4 J hat plus 3 K hat, then adding them is super easy. S, the sum, is equal to A plus B, is just literally 3 plus negative 7 I hat plus 4 plus 4 J hat plus 0 plus 3 K hat. Notice I didn't put any units on it. It is okay to have a vector that truly has no units, but it's quite often quite normal to have units of like 3 newtons, 3 meters, 3 meters per second, or whatever. But the main thing is now that I've added these like components, 3 plus negative 7 is negative 4. So I got negative 4 I hat. 4 plus 4 is 8. So that's plus 8 J hat. And 0 plus 3 is 3. So that's plus 3 K hat. And that's how much easier it is to add vectors now that we're using the IJK notation. I will also say that it is also allowed and perfectly reasonable to write this as negative 4 X hat plus 8 Y hat plus 3 Z hat. In other words, uh, X hat, Y hat, and Z hat are perfectly acceptable versions of I hat, J hat, and K hat. Additionally, I could also write this as negative 4, 8, 3. Notice how in that case it's just like a point, where a point would be left parenthesis negative 4 comma 8 comma 3 close parenthesis. When you're doing an actual vector, you can indicate that it's a vector as opposed to a point by putting it in a less than and greater than symbol. So that's sort of all the bells and whistles associated with addition and subtraction of vectors. So anybody have any questions on any of that now? All right. So what I'm going to tell you is you can solve projectile motion problems because that's where we're going now. You can solve projectile motion problems once you understand one basic fact. And I normally would put up this photo from the book, but it seems I've got to contact my textbook publisher because all of a sudden it's not allowing me access to the ebook, even though I'm the teacher. So, so that's a real problem because obviously I need the ebook. I don't even bring a book back and forth to anymore. I happen to have an old edition of a Giancoli. I probably got a second edition in here somewhere, but I can't access it. So because of that, I can't access a really important drawing, or excuse me, a really important figure. In your book, there's an important figure, and it's basically a red ball and a yellow ball. And I can't remember what the red ball is doing and what the yellow ball is doing, but one of them does one thing and the other one does the other thing. So what it is you have two balls and they're sitting at exactly the same height, and it's supposedly in a really dark room, but about every tenth of a second, it might even be hundredth of a second or something like that, a light flashes that brightens up the whole space, and then again, another tenth of a second later, another one flashes and another one flashes and another one flashes. Each time that happens, that actually leaves an image of the scene at each of those time intervals. And lo and behold, what you'll see is the red ball and the yellow ball, one has been launched horizontally and happens to be exactly the same height at each point in time, even though it's moving horizontally to the right, say, while the other one's falling straight down. That is a monumentally important discovery. Specifically, what that tells you is that when you're dealing with an object on near the surface of the Earth, you're going to have a gravitational acceleration in the downward direction. And it turns out that the downward acceleration in the y direction plays no role whatsoever in affecting the motion of the horizontal motion. So you can keep the fact that it's accelerating completely separate. In fact, the way I tell my students to imagine a projectile motion problem is you just imagine that horizontally, uh, you can represent projectile motion as if it were the shadow of a ball flying at a constant horizontal velocity over the area where the projectile is fired. And in that scenario, of course, you got to imagine the sun's directly overhead, so the shadow of the ball is actually directly below it. But what you see is that shadow moves at a constant speed from left to right, say, the whole time the projectile is in the air. And that's always going to happen. And that speed that it travels horizontally is called the v component of the initial velocity. On the other hand, if you imagine a system of lasers, all set up parallel to fire parallel beams of light, maybe, 1 centimeter apart, and you've got them stacked, on top of each other so that they span a whole, 100-meter height. And what you'd see is all of those little laser beams are shooting perfect little laser red dots on the wall. But when the ball is actually fired as a projectile, there is a component of the motion that's horizontal, and that's covered by that shadow we just talked about. But if you imagine the lasers are far enough off where they're not actually going to get hit, or the actual projectile is not going to fire from one side of it and then land on the other side of the lasers or anything like that, they're going to be far away. What you'd see is that the vertical motion of the projectile would be shown by the lasers as an object that goes up, accelerating downward at 9.8 meters per second every second until it reaches some max height. And then it starts to fall back down at, again, that same 9.8 meters per second downward. And that motion is completely independent of the horizontal motion. So that's the key to solving projectile motion problems, is you first off have to break down your launch velocity into X and Y components. And then the X component is going to just move constantly with no acceleration because we're ignoring air resistance. But the Y component is going to start off with that Y component that it has initially, and it's going to slow down from there. So it's fired upward usually. It could actually be fired downward too. But the main thing is the acceleration is going to be downward. So even if you fired it downward, what would happen is the speed downward would actually increase by 9.8 meters per second each second, or you could say by 0.98 meters per second every second, if you did it every tenth of a second. So that would, make it a little easier to see. But the main thing is that acceleration is going to be constant, so that if you imagine, for instance, the initial vertical velocity was 3 times 9.8, which you might remember is 27.4, if I remember. 29.4, excuse me. So if you imagine some projectile that was fired at an angle, and then you computed the vertical component of the velocity initially, and you found that that vertical component was 29.4 meters per second, what you'd find out is that it would fire upward from whatever height it is, traveling at 29.4 meters per second. But after 1 second, it would slow down to 19.6. And then after another second, it would slow down to 9.8. And then after another second, it would slow down to 0. And then after another second, it would actually be speeding up to negative 9.8. So it's actually the velocity is getting more negative. But in this case, it's actually, increasing its magnitude, because at the peak of the motion, its velocity was 0. And then 1 second later, it's 9.8, but downward. So we'd call its velocity negative 9.8 in the Y direction. Then after another second, it's negative 19.6. And then after another second, it's negative 29.4. And if you were to catch it at that point, you would catch it at exactly the same height it was fired from. But if you were to let it go, it would then increase its velocity by another negative 9.8 meters per second the next second, and another 9.8 thereafter. So that's the key to understanding how projectile motion occurs. Does anybody have any questions on that? All right, so what I'm going to do is work with this in our kinematic equations and give you an example of the sort of the most generic projectile motion problem possible. So here is a nearly completely generic projectile motion problem. So projectile will be fired with initial velocity v0. What I'm going to do is I'm going to draw a coordinate system just because it's easier to deal with once you have a coordinate system. I'm going to draw a coordinate system just like this. Okay. And I'm seeing it's nearly completely generic. It's not generic in the sense that I'm going to fire it from a certain height, which is going to be the origin, and it's going to reach some max height, and then it's going to land at the same height that it was at before, and that height will be exactly the same elevation as it was fired at. So in that sense, it's not that generic, but what the actual motion is going to be is something like this. And what we can do is we can say, well, right here, this is the initial velocity v0. And of course, the initial velocity being v0 means the magnitude is actually v0. So explain the outcome of a projectile fired at v0 equals v0 and theta degrees, oops, above horizontal. So now that we have that, I can also specify that this angle right here is theta 0. I am going to tell you that this height right here is going to be called H max. And this distance right here is going to be called R, which means the range. And in fact, this is the final velocity. Uh, which we could say, I'm going to draw the black axis like this. There's my x-axis. I'm going to redraw that final velocity vector a little neater than that. Okay. And what I'm saying is this angle right here is going to be the angle phi. And the magnitude would just be V equals question mark. Okay. So that's the actual projectile we're trying to, projectile motion we're trying to solve. Okay. Everybody sees that it has an initial velocity v0 and it's fired at an angle theta above zero angle. It's fired from the origin and it lands at exactly the same height that it was launched from, so that you're not considering launching, for instance, off of a hill or landing up on a hill. That makes a lot of the calculations a lot easier, and I'm going to go with that now. So first, I'm going to say step one, break the initial velocity down into x and y components. So here's my explanation of that. What we have is a x-axis and a y-axis. And we have a velocity whose magnitude is v0 and whose angle is theta. Now I can tell the shadow cast by this vector onto the horizontal axis is in fact our x component, and we could call that an actual vector, and that would be called v0 sub x with a vector symbol over it. And with the vector symbol over it, it would be the magnitude and the units, which would be meters per second, and it would have an I hat next to it. Otherwise, it'd just be the magnitude times meters per second. Now, it is pointing in the positive direction, so that's why I chose to draw it red. Similarly, the y component is also drawn as red because it too is in the positive direction, and that one's called V0y. Now, in order to do this, as I told you, when you first start dealing with these vectors, it's best to just go ahead and take the time to write out sine, write out cosine, and then figure out which one, sine or cosine, is going to give you the x component and which one's going to give you sine or cosine, which one's going to give you the y component, and to choose whether or not those components are positive or negative. In this case, they're both positive. So to do this, I'm going to say the sine of theta, which remember, some old horse came a hopping through our alley, or so katoa. So some old horse would be sine equals opposite, which is V0y, over hypotenuse, which is just V0, and cosine theta is came a hopping, or ka. So came a hopping is cosine equals adjacent over hypotenuse. Again, the adjacent angle, or excuse me, the adjacent side is the side touching the angle. The opposite side is the side that's not touching the angle, and the hypotenuse is the longest side, and the right angle sort of acts like an arrow pointing to the hypotenuse. So if you have any difficulties figuring out which are which with right triangles, remember you can put that right angle there and let it be treated as the head of an arrow, and then it's pointing to the hypotenuse, which is this guy. So cosine is going to be adjacent, which is V0x, over hypotenuse, which is V0. So we're able to get from that V0x is equal to just V0 cosine theta, and obviously that's positive. Similarly, we're able to find that V0y is equal to V0 sine theta. Okay, that's it. That's the main thing that we have to do. Now, step 2, use the main x of t kinematic equation to locate y of t and x of t for the projectile at times t. So that might sound kind of complicated, and this is one of those cases where the wording and saying it makes it way more complicated than just doing it. So I want you to understand that that's quite often the case. So what I mean by the main kinematic equation, remember when we took A equals a constant and we integrated that twice, the first time you integrate using A is equal to dv dt, and you end up getting V equals V0 plus AT because you allowed for the idea that the velocity at t equals 0 was V0. And then having found that V, meaning V of t, is equal to V0 plus AT, once we found that, we could set that equal to dx dt, integrate that, and then use the fact that at x, or excuse me, at t equals 0, x should be equal to x0. And when that was all said and done, we were able to come up with the following equation, and that is x is equal to 1/2 a t squared plus v0 t plus x0. That's sort of the fundamental or the main kinematic equation for acceleration being a constant. In terms of the x motion, though, the acceleration is 0. So, however, a sub x is equal to 0, and x0 is equal to 0, because notice, remember, on the original drawing here, I put that the projectile started at the origin, so that x0, y0 is equal to 0, 0. Because of that, x0 is going to be 0, and because we're ignoring air resistance, the acceleration in the x direction is 0. So now we can write the equation x, which is literally the position, the x position as a function of time. We can write this as x of t is equal to, now v0 is v0x. So because of that, we're going to say that we have V0 times t times the sine of theta, or excuse me, times, it was supposed to be x, so it's supposed to be cosine of theta, my fault, times the cosine of theta. Now notice I put the t between the V0 and the cosine, because if I put the t after the theta, there might be some confusion as to whether the cosine is being taken of theta or theta times t. And I don't like using parentheses, so I just assume write it as V0t times cosine theta. So notice the V0 times cosine theta is the actual x component of velocity. Notice the x0 was 0 and the acceleration was 0. Now we have the same thing for the y equation. Now specifically, this is a sub y t squared plus v0 y t plus y0. However, oops. However, a y is equal to negative 9.80 meters per second every second, which is negative g. And y0 is equal to 0. And v0y is equal to v0 sine theta. So what I'm going to get for this one is y of t is equal to negative 1/2 gt squared plus v0t sine theta. So this equation and this equation will give you the x and y position. So you can find the position, parenthesis, x of t, comma, y of t, close parenthesis, at any point in time, just by plugging these in into an ordered pair, where the x is v0t cosine theta and the y is negative 1/2 gt squared plus v0t sine theta. So that's the step 2 of the solving projectile motion. Now we can just start using these results to figure out various parameters. So step 4 or step 3. Now we apply logic and reasoning to find what the max height, range, max range, final velocity, so we're just going to use basic principles that we've learned from projectile motion or from motion in general, kinematics specifically. We're going to use that to try to ascertain some of the things we asked about. So for instance, we might want to say, what is the max height? All right, let's do that in blue. And actually, since we labeled it already, I should say max height, and then I'll write comma H max. Okay. So one thing we could think about it is it literally says the max height. The max height means hey Shawnee, Corby's here, baby. All right, I'll tell you what, I've got a visitor. This would be a perfect time for us to go ahead and take that 10-minute break. So we'll be back at 6:52, and we'll finish this up. Thank you. I'm here if you have any questions, but go for it. Obviously, my notes are going to keep you organized. It's okay, Shawnee. I just went ahead and took a break. Well, I have to give him a break anyway, so. Oh, that's nice of him. Oh, it's a bundt cake. I love that.
Dan was going to speak last Sorry.
That's fine, baby.
Did she do it?
I don't know if she went and bought it and just delivered us a cake. Oh, you didn't see her? Okay. Yeah, she walked out a second ago. That's why I called you and told you to report you.
Of course somebody's going to name.
And oh my boy, this little puppy is very interested in sniffing this, Mama. It's my birthday, everyone. So the neighbor just bought me a cake. Ooh, she bought me a bunch of cupcakes. Ooh, red velvet.
You too little?
Mhm.
Holy cow.
Oh, I think I'm gonna take a brown one.
I absolutely told her to try to stay away from chocolate. And you got excited and said red velvet, and then you took the chocolate one.
Yeah.
I wonder what that one is. Chocolate, vanilla, red velvet. What do you think that is?
No, this one's good though.
Mhm.
My little umbrella.
Okay. Well, we have to make sure that you text her. Should have taken a picture before we became together.
I'll roll, you knew that. Hey, Chase. Oh, I saw you, buddy. Hey, everybody, this is my little buddy Chase. Evidently, I was a little too rough when I tried to pick him up. What's up, buddy? You want to go get those skates? Okay, you go get the skates. Come here, Cosmo. Come here, Cosmo. Cosmo thinks it's a trick, so I couldn't show you him. Yeah, I've seen him once, I think, already. But anyways, is that good?
Fine. Okay.
Mm.
You gonna eat it?
Got some strawberry in it. Oh, that was even better. I was hoping Cosmo would come. Come here, Cosmo.
Wait. Well, you gotta act like you're giving them.
Oh.
I don't believe it. Jeez.
Come here, Cosmo.
Jeez.
Cosmo. Come here, buddy.
You're tired.
Touch. Well, I already had Jay here. Okay, Cosmo.
Good boy.
Get here, my Cosmo. Hello, everybody. Say hello to my little buddy who's very interested in the food that's going down and not interested in anything but the food. But I wanted to show you how good of a boy he is, and clearly he's a great boy. He's not really. He's a turd. He's a good boy. Okay. You're rolling something stinky, though. Ugh. All right, we got about 6 more minutes. Thank you, Ayana. I am 55 today, everybody. I'm super old. Pretty soon they're going to start asking me if I get a senior discount. And I'm going to tell them no. Leave me alone. Hey there, Chase. What's up, buddy? I wasn't sure how long that would take, so I went ahead and gave y'all a full 10-minute break. That's not a problem for me, though. Like I said, we got a little bit more time to finish this, and you're going to get some really good results here, and this teaches you a lot. I'm going to go ahead and finish that sentence I was writing when we decided to take a break. So the max height means the maxima of the y of t. So one way we could actually think about that is in terms of the maximum. So that's why I was writing the sentence, but we'll finish it up again when classes returned. Yes, it is today. I'm a speed limit. I used to be the max speed limit in all of the United States. Not anymore. All right, got one more minute. All right, it's about time. Let's go ahead and get started. So, as I was saying, we are in the process of solving this general slash generic projectile motion problem, which can be stated basically with this drawing and the black sentence above it, which says, explain the outcome of a projectile fired at V0, the initial velocity, has a magnitude of V0 and an angle theta degrees above horizontal. And specifically, I'm asking for the max height, the range, and the final velocity. So I told you the first step when solving a projectile motion problem is to break the initial velocity down into x and y components. I've done that. The second step is to use the most fundamental of the kinematic equations, the x equals 1/2 at squared plus v0t plus x0 equation, to fashion basically an x as a function of time and a y as a function of time for the projectile. And I showed you exactly how to do that. All you have to do is remember that the acceleration in the x direction is 0, and that the x component of the initial velocity is v0 cosine theta. So you can put that in there. And in our case, we said x0 and y0 equal to 0. So we didn't even have those terms. But either way, that was it. And then step 3, it says now we apply logic and reasoning to find what the max height, range, max range, final velocity, and dot, dot, dot are. So I'm in the process of explaining that, and I said the max height means the maxima of y of t. I mean, it literally means max height, so of course it would be y of t. Does anybody recall from calculus how you find the maxima of a function? Anyone? I'm checking the I'm checking out the chat just in case anybody answers. No one knows how to find the maxima of y as a function of t. So this happens to be just one of the ways, as you realize that y is a function of t, and the max height obviously is setting y equal to 0, setting the derivative of y with respect to with respect to t equal to 0, and that should allow us to solve for the time at which it's 0. Then all I have to do is plug the time at which we found the maxima into y of t, and that'll tell us what y is at that time, and that y at that time should be h max. So following that train of thought, let's work the problem as I just explained it. So I'm going to say dy of t over dt equals 0. Now that means d by dt, and our y of t was negative 1/2 gt squared plus v0 t, and then of course we were talking the y direction, so that'd be sine theta, like that, and we're going to set that equal to 0. The derivative of this with respect to t is negative 2gt, or excuse me, negative gt, because the 1/2, the negative 1/2 is going to cancel out with the 2 that comes down from taking the derivative of gt squared. So this is going to be negative gt plus v0 sine theta is equal to 0. Therefore, we conclude that t is equal to v0 sine theta over g. Notice when I pull the gt to the other side, it becomes positive. Then I divide both sides by g, and that gives me t on one side and v0 sine theta over g on the other. Now I plug that in, because h max, what we're looking for, is just is just y of t max. And I just called that T max, meaning the time at which maximum height occurs. It's not the maximum time. It's not the time that it's in the air or anything like that. I just chose to call it that. So now I can just go back and plug this into my y as a function of time, which is going to be negative 1/2 g. Now, in place of t squared, I'm going to put v0 sine theta over g quantity squared plus v0 times v0 sine theta over g times sine theta like that. And simplifying a little bit, we can see that when we square the v0 sine theta over g, we get a g squared in the bottom. That's going to cancel out with the g in the top and leave a 2g in the bottom. So I'm going to say negative, and I'm going to put a 2g down at the bottom. But on top, it's going to be v0 squared sine squared theta. And then for the next term, that's going to be v0 squared sine squared theta. But this one's actually over just plain g. So I'm going to multiply top and bottom by 2. And when I do that, now I will get 2v0 squared. Notice it's positive. The one with the 2 in front of it's positive, so I'm going to write it first. So it'll be 2v0 squared sine squared theta minus v0 squared sine squared theta. They both have the same denominator now, so that's why I just wrote them as one big fraction. That'll be 2g in the bottom. 2v0 squared sine squared theta is just going to be minus v0 squared sine squared theta is just going to be v0 squared sine squared theta over 2g. And if you look at that, the units for V0 would be meters per second. And then when you square it, it'd be meters squared per second squared. And then if you divide that by G, G has units of meters per second squared. So you're just going to get meters out. And that's exactly what we expect. So we can go ahead and write that H max is equal to V0 squared sine squared theta over 2g, and that is the general solution for the max height of a projectile, assuming that you fire it and it travels and lands at the exact same height or over the exact same height at which it was fired. So long as the launch point and the landing point are the same heights, the max height would be just this quantity, v0 squared sine squared theta over 2g. We also could probably reason that this is the T max, the V0 sine theta over G, is the time required for it to reach that max height. If we look at the original problem, I think you could see that this time right here is by symmetry, it looks like it would be the halfway point, meaning if I took the time that we called T max, which was V0 sine theta over G, if I took that and multiplied it by 2, that should be the time that it was aloft. In other words, the hang time of the projectile would be twice T max. Now, I'm not going to go on that assumption. I just know it from the symmetry. It looks like it'll be true, but we can use that as well to check our reasoning when we finish solving for the other variables. So one of the other variables we'd solve for, of course, would be the hang time or the time aloft. So we already did the max height. We still want to do, for instance, the final velocity. I would also like to find out exactly how long it's in the air, because the way projectile motion works is the vertical component of velocity tells you how long you get to stay in the air, and then the horizontal component of velocity is the one that tells you how far you can go horizontally while it's in the air. So if you actually figure out the time aloft, all you have to do is take that time and multiply it by the x component of velocity, and that'll give you the range. So I think that's the next thing I'm going to solve for, is the range. So B. what is the range of the projectile? And that quantity is called R. By the way, I didn't tell you another way of doing part A, which was finding the max height. I did tell you it was a maximum, so that's one way. Another way you could do another way you could find the H max is you say, okay, well, I know the object is thrown up with an initial y component of velocity given by v0 times sine theta. So what I'd like to know is basically how long will it take for that velocity in the y direction to become zero. So if I could actually find y velocity v sub y of t, then that would give me the velocity as a function of time, and I could just solve for when that velocity is equal to zero, because when the vertical component of velocity equals zero, that's the time at which max height occurs. So I could do that by setting v of t, which you got by taking dy dt. But when you take dy dt, you get v sub y of t. You could take that v sub y of t, set that equal to zero, and that would tell you the time that it reaches the max height. That would give you t max. You then could plug that in y of t, and you'd get exactly the same answer, v0 squared sine squared theta over 2g. So hopefully that helps you. I'll write that here. Alternatively, Vy of t is equal to dy of t over dt, and t max occurs when Vy of t is equal to zero. So again, that will give you another option to solve for t. So now to find the projectile, what I'd like to know is how long is the projectile in the air? Aloft. This is called THC, which equals hang time. So in terms of college football and NFL and that sort of stuff, you've probably heard the phrase hang time again. That's what we're solving for, is the hang time. So one of the ways we can solve for this is by asking how long is the projectile aloft? Well, the projectile is aloft when basically when y of t is equal to zero. There's one time where y of t is equal to zero, specifically at t equals zero. That's not the one, but there's another time later where t is not equal to zero, and that is the one. So what I'm going to do is I'm going to take y of t, which we know is negative 1/2 gt squared, plus v0t times the sine of theta. I'm going to set that equal to zero. By setting it equal to zero, then I can automatically look and realize I can factor out a common term of t, or a common factor of t, from these two terms, and that's going to give me t times, now I'm going to say v0 sine theta minus 1/2 gt is equal to zero, and this implies t equals zero, or v0 sine theta minus 1/2 gt is equal to zero. Now this being equal to zero gives us that t hang time is obviously equal to 2 v0 sine theta over g, which is exactly what I told you, because remember we suggested that the time to h max was v0 over g. I said if we multiplied that by 2, that should be the time aloft, and now we see there's t max and there's t hang time. So now here's another result you can use. And I say you can use this. What I mean by this is you can use it if you memorize it. I'm not putting it on your equation sheet, but if you go through the process of deriving this, I suspect you'll have it memorized. But the result is t hang time is equal to 2v0 sine theta over g. Now that we have that, I can find out R. So R is equal to x of t hang time. And x of t hang time is just v0 times t. So I put in 2v0 sine theta. That actually it looks fine. I guess I'll leave it over g times, of course, this was cosine theta there. So what you see is we get 2v0 squared sine theta cosine theta. Well, it turns out that 2 sine theta cosine theta is the same thing as sine of 2 theta. So that's a trig identity that you can look up yourself. I'll double check it right now. So 2 sine theta times cosine theta is equal to sine of 2 theta. Yep. So what I can now say is that R is equal to, remember I said 2 times sine theta times cosine theta is equal to the sine of 2 times theta. That's what I'm using here. So I'm going to have V0 squared sine 2 theta over G. And that should give us a distance in meters as well, as it does. And this also tells you a little bit, because remember the angle, the way we define the projectile angle that it's fired at, the theta has to be between 0 and 90. It doesn't make any sense for it to be anything bigger than 90. So if you look at the sine function from 0 to 90, you realize that the 2 theta gives you two chances for all but one particular value of sine of 2 theta. And that particular value is the peak that occurs. And that peak, of course, maximizes the R. So it makes a maxima of the range. And therefore, it occurs when the sine of 2 theta is equal to 1. And the sine of 2 theta is equal to 1 when theta equals 45 degrees. And the fact that it has 2 thetas that give you the same sine of 2 theta means there's a high trajectory and a low trajectory for all but the max height or the max range that you fire it. So now I can go ahead and say this, and just pointing out again what I'm looking at here is if this is R and this is theta, what you find is this function R of theta looks like this. This theta occurs at theta equals 45 degrees, which of course is also, remember, pi is 180, pi over 2 is 90, so this would be pi over 4. But if you look at any other value that you'd like R to be, then it has two angles, theta 1 and theta 2, and theta 1 and theta 2 differ by the same amount from 45. Specifically, that means 45 degrees minus theta 1 is equal to basically some number. but that number happens to be the same thing as theta 2 minus 45 degrees. So that's how the two uh, different trajectories work. So if you're looking at high trajectory, you'd want the some angle above 45 degrees. If you take the same angle below 45 degrees, then you'll be shooting for the low trajectory. This is, for instance, a lot of bad free throw shooters in NBA and college basketball. I'm thinking Shaquille O'Neal in terms of NBA. But specifically, a lot of bad free throw shooters are bad because they use the lower trajectory. There's just a little bit higher probability of it making it in with the higher trajectory, I suspect, though I haven't done any studies on that specifically. All right, so we now have the range, we have the hang time, we have the max height. What we might want to figure out now is what is the max or what is the final velocity. So that's part C. So what is the final velocity? So remember, you can use what I hinted at was another way we could have done that first part where specifically y of t is, and I'll write it in a different order than I did before. It's going to be v0t sine theta minus 1/2 gt squared. That's y of t, but v sub y of t is equal to dy over dt. So from that, we can say that v sub y of t is going to be v0 sine theta minus gt. Okay, so that's the actual y velocity as a function of time. If I wanted to take another derivative, I could actually find out what the y acceleration as a function of time is, and you'd see that that would give me, of course, negative g. But that's not really needed here. I just wanted to point that out to you. So what I'm going to first find out is what is the final y component of velocity. And I will use the fact that the initial, or excuse me, the x component of velocity doesn't change because there's no acceleration in the x direction. So the y final of t is v, excuse me, that is vy of t hang time. So that's all I have to do to find out what the final velocity is. I just need to plug in the time for v hang time. Well, that's v0 times the sine of theta minus g, and now the t for the hang time is 2v0 sine theta over g. Let me double check my math. 2v0 sine theta over g, 2v0 sine theta over g. That is the hang time, so we're right on that. We can see that the g's cancel each other out now, and we can also see that the result is v0 sine theta minus 2v0 sine theta, which is equal to negative v0 sine theta. That's pretty amazing. That's telling us that the y component of velocity is literally just the negative sign of the initial y component of velocity. The initial y component of velocity was just v0 sine theta. This one's negative v0 sine theta. The projectile experiences no acceleration. Oops. In the x direction, so that Vx of t is a constant. Vx of t is dx of t over dt, which is d by dt of, remember we got v0 t cosine theta. That was the entirety of the x of t, which we got right here. X of t equals v0 t cosine theta. I used this one earlier. So now that I use the v0 t cosine theta, the derivative of this with respect to time is just v0 cosine theta, and that's the constant that it is. So we can say, whoa, no, just erased everything I was writing for no apparent reason. Therefore, the final velocity is, let's say, v final is equal to, now the x component is going to be v0 cosine theta, and then I'm going to just put that in the I hat direction, plus negative v0 sine theta j hat. That is the final velocity for this. Now, of course, uh, you could do that even if the initial position and the final position weren't the same height. You would still do the same thing. You would set y of t equal to 0 and then solve for t, but you get it something different than the normal hang time. Another thing to notice about this is if you actually place this final velocity in an XY coordinate system, I'm going to do that now, you'll see what the actual angle is. I called the angle phi in my drawing, but you're going to see that the phi is actually closely related to theta. So this is my y-axis, this is my x-axis. What we found was the x component of velocity was just v0 cosine theta. So this quantity was v0 cosine theta. And then I had another component. This one was actually a negative component, so I'm going to do it in green like I did before. And this one's going to be negative v0 sine theta. That means the final vector, v final, makes an angle, specifically an angle phi with respect to the positive x-axis. Now this angle, since we're doing it clockwise, it would technically be a negative angle, but let's see what it is. So phi is equal to the inverse tangent of opposite over adjacent. So the opposite is, in fact, I'm just taking the magnitudes here, not the signs, v0 sine theta over v0 cosine theta. Obviously, you can see that the v0s cancel each other out, and that the sine theta over cosine theta just becomes the tangent theta. So it's the inverse tangent of the tangent of theta, which means phi is just equal to negative theta. So that is actually the symmetry of the projectile motion, is that it would, if you launch from one height and you land at exactly the other height, the same height, then the final velocity, just a split second before it hits the ground, will in fact be exactly the same magnitude as the original velocity, but instead of being at an angle positive theta, it's going to be at an angle negative theta. So that's a pretty big deal. Anybody have any questions on that? No questions? All right. Well, we've got a little while left. I'm going to show another traditional vector problem, or projectile motion problem. In this case, I'll go ahead and write it to say you plan to sedate a monkey by shooting it with a tranquilizer dart, but you know that at the instant the monkey hears the shot, it will let go from the branch on which it hangs. Oops. Should you aim that's a really bad looking aim. Should you aim above, at, or below the hanging monkey? Anybody think they know an answer to that? Do you aim above, below, or directly at the monkey? By the way, y'all might want to go ahead and chat me your first and last names. So we'll go ahead and have those. Remember, if you're in O01B, to either write O01B with your name or just go ahead and just say asynchronous or something like that with it. So I'm going to go ahead and draw this out, and I'm going to use numbers specifically. Uh, and then we're going to use that to solve and find out specifically exactly what the answer is. So what I'm going to do is I'm going to imagine a projectile fired at a velocity v0. And let's say this velocity is 10.0 meters per second. I'm going to say the angle theta is the question mark. And I'm going to say that the monkey okay, so the monkey is hanging right here. Okay, and I'm going to say that this height right here is, let's say, 15.0 meters. And let's say this distance right here is 25.0 meters. Okay, oops, that shouldn't go all the way there. That should go right here. Okay. So I want to figure out at what angle theta I should fire this so that it'll hit the monkey. But what I know is going to happen is the instant that I pull the trigger, the projectile is going to take off from right here. Remember, it's right here, not here. It's not taking off from here, it's taking off from here. And I want it to do like this. And of course, gravity's going to act on it. But if it's going really fast and gravity not so much, it might hit the monkey here. But if gravity is really, really fast and the tranquilizer dart is really, really slow, it might hit the monkey way over here. But the main thing is I need to hit the monkey. So in order to do that, I need x of t and y of t for the monkey and for the projectile to be the same at the instant that the projectile gets to the x equals 25 meters. So in other words, if I wished, I could go ahead and call this the positive x-axis and this the positive y-axis. So, solution. As I said, what I'm going to do is I'm going to have monkey coordinates and I'm going to have dart coordinates. So dart. The dart is going to have x of t is equal to 10.0 meters per second times cosine theta. And it's going to have y of t is equal to negative 4.90 meters per second t squared plus, let me go ahead and use this on the next line. So I'll say plus 10.0 meters per second times t times, in this case, it's the sine of theta degrees. Okay. And both the projectile, the projectile has both x0 and y0 equal to 0. That's why there's none on there. Now for the monkey, its x as a function of t is just going to be 25.0 meters. Nothing's going to change on that whatsoever. He's always going to be at 25.0 meters. Now, the y of t is going to start off at 15.0 meters, but as soon as it hears the sound, and we're going to assume that the speed of sound is way, 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 way faster than the speed of the tranquilizer gun, in which case it's like instantaneous report of the weapon firing and the monkey drops. And once that happens, the monkey is going to start to fall with an acceleration equal to that of gravity, and therefore it'll be a negative 9.8 meters per second every second. So this is going to be for y of t negative 4.90 meters per second every second. Make sure everybody sees that that is a 4.90. Meters per second times, notice that's negative 1/2 g, that's why it's 4.90 instead of 9.8, and this would be t squared as well. And again, in this case, the initial height was 15 meters, that's why that's out there. There is going to be no initial velocity in the y direction, so that's why I don't have a v0t term there, but that's it. In order for the projectile to hit the monkey, then when the monkey's x position is 25 meters, we have to have, or excuse me, when the tranquilizer dart has an x coordinate equal to 25.0 meters, it should have the same y coordinate that the monkey does, and then it will be hit. So all we have to do is make that happen. So I'm going to say at what time is the dart at x of t equals 25.0 meters. So do that. All I have to do is take 10.0 meters per second times cosine theta is equal to 25.0 meters. That means, oh, there's supposed to be a time in there too. I forgot the time that's supposed to go between the 10 meters per second and the cosine theta. So let me fix that real quick. Hopefully y'all all caught that already, but if you didn't, make sure you change it now. So this is 10.0 meters per second times t times cosine theta. And I did remember the t on the y one for the dart, so that's good. So in this case, I'm just going to put the t out in front. And since I didn't put it between it, that's okay. That means t is equal to 25.0 meters over 10.0 meters per second times, in this case, it's going to be a cosine in the bottom. So 25 divided by 10 is going to give 2.50 seconds divided by cosine theta. And that's going to be the time at which it hits the monkey. So I'll just call this T25. And it specifically means the time at which the dart is 25 meters to the right of where it was. Anybody have any questions on this part? Okay, so now I've figured out the time at which the dart will be at 25 meters. Now I've got to make sure the two y's for the monkey and for the dart are equal to each other at that time. So at t equals t25, y dart equals y monkey. So plugging that in, what I'm going to get is negative 4.90 meters per second times t squared. Oops, that's times t. So I actually know what that t is supposed to be. I'm going to plug in 2.50 seconds over cosine theta, and that's supposed to be t squared from the dart's y of t. And then it'll be plus 10.0 meters per second times t, which is 2.50 seconds over cosine theta, times, in this case, it'd be sine theta. So that's the y dart equation. I seem to have copied everything correctly there. Now the y monkey equation is going to be equal to 15.0 meters minus 4.90 meters per second times t squared, which would be 2.50 seconds over cosine theta squared. Now, the big thing is to notice that those two terms are identical. So I can add positive 4.90 meters per second times 2.50 seconds squared over cosine theta squared to both sides, and they will just disappear. Now all I have left is basically I can take the 10, I can take the 15 and divide it by 10. So on the left-hand side, I'm going to get sine theta over cosine theta. So notice what I did was I used this sine theta and this cosine theta. And of course, sine theta over cosine theta is actually equal to tangent theta. So I'll go ahead and say that. But now what I'm going to do is divide both sides by 10. So I'm going to divide by this 10 meters per second. And then I'm going to divide by 2.50 as well. And that's seconds, of course. So I'm going to get 15.0 meters. That's going to be over 2.50 seconds times 10.0 meters per second. And what we see here is 2.5 times 10 becomes 25.0. So I got 15, oops, better stick it to the red, stick to the red pen, 15.0 meters over 25.0 meters, which equals, or I should say, therefore, theta is equal to the inverse tangent of 15 over 25, which is aiming exactly at the monkey. Because you can see this triangle, let's do this with a laser pointer. This triangle has a height 15.0 meters and a width 25.0 meters. So this angle theta is the inverse tangent of 15 over 25. Anybody have any questions on that one? Okay, so that's a pretty robust projectile motion problem. You can, of course, look at the other examples in the book as well. I think these two examples work really, really thoroughly and with a lot of mentioning all the details. Hopefully that will help you. Does anybody have any questions on any of this? So I just want to remind you guys, you do have a face-to-face test one. If memory serves me, again, I'm referring you to go back and look in Canvas to make sure I'm right about this date, but I think it's Monday evening at 11:59 p.m. is when you have to have it done. And if I'm not mistaken, that Monday evening would be June 9th, and it covers some fundamental questions about projectile motion, like about the acceleration being 0 in the x direction, the acceleration being a constant for the entire motion of the projectile. Uh, some minor concepts like that is about all I would ask you about projectiles, but all the vector addition stuff is completely fair. So you need to know how to break vectors up into components. You have to be able to figure out whether the component is positive or negative. You have to know whether to use sine or cosine. You have to know how to use it so that you can actually get the right sign for the components. You have to be able to add vectors. You have to be able to subtract vectors. You have to be able to add vectors graphically with the two vectors tail to tail. You have to add vectors graphically with the two vectors head to tail. You have to be able to subtract vectors with the two vectors tail to tail and subtract vectors with the two vectors head to tail. All of that stuff is completely fair game. The main thing is, as I said, you have to get this test done. If you find out that you're running out of time, you don't have an appointment that can fit in your schedule or whatever, make sure you let me know. Ideally, this would be something you let me know like by Sunday. I really don't think I should hear from you guys on a Monday when it's due on a Monday, but that might actually happen. But you should know by well before then anyways. But try to get it done. If you don't, I will work with you. We'll try our best to make sure you can get it done in a timely fashion without being too much of a delay. So good luck on that. Make sure I did not make, for instance, I didn't make a specific practice test that's listed for the final for the face-to-face test. This time, in lieu of that, you have practice test 1, which is on chapters 1 and 2, and you have practice test 2, which is on chapters 3 and 4. So basically, practice test 1 is definitely a practice test for the face-to-face test 1. practice test 2 is sort of a practice test for face-to-face test 1, but to be honest with you, it's really only the first 25% of the test of the practice test 2 that's for it. If you want more practice on chapter 3, just go to the chapter practice, which is above the online tests and practice tests, so you can do those. Remember also that I did move the homework dates to like the 9th, but I am planning on moving them back probably at least 3 or 4 days, but I might even do a whole week. So I'm definitely not going all the way back to the 23rd or anything like that, but I think I am going to push it back. So thanks for coming, everyone. I'll wait for the last person to leave in case anybody has any questions, but you are free to go. Make sure you've already chatted me your first and last name and whether you're in the synchronous class or not. I just saw, wait, does test 1 have vectors in it? The online test didn't have any vector questions on it. Yes, the first online practice test didn't because that's just chapters 1 and 2, but this face-to-face test will have vector addition in it. That's absolutely it. That's why I said it's really important that you try to take practice test 1 and practice test 2, or if you're bummed out about practice test 2 wasting information on the second half of chapter 3 and chapter 4, then just do the practice quiz for chapter 3. That would be more than enough to prepare you along with the practice test for chapters 1 and 2. Sorry about that, Eli. Anybody else have any questions? Well, thank you for coming, everyone. Remember, I do have a testing time tomorrow that anybody can show up for. You're supposed to email me, let me know that you want it. I did get a couple people's emails, but you're supposed to email me, let me know that you're coming. If you want to, that's fine. Go ahead and come, but make sure you just email me, let me know. You should show up in my the JC Hall in Building J on the Virginia Beach campus, and you should be prepared to start taking it by 12:45 p.m. tomorrow. Okay. That being said, we did find out that Dr. Johnson's willing to proctor some tests. So by all means, contact him. Make sure he's willing to do that for you. And if he is, then plan on taking it with him during your normal lab. And that would be awesome if he does that for you. Thanks, everybody. Yes, the Eli, it covers 1 through 3, but it doesn't cover all of chapter 3. Like I said, I think I might have put a couple conceptual questions about projectile motion, but other than that, there's no projectile motion. It's just vector addition from chapter 3. That's the only part of chapter 3 that's in there. Anybody else?
I have mainly different problems with because I'm basically a chapter behind.
That's that's pretty normal at this point. Luckily for you, you have until Monday to take the test, so I wouldn't worry too much about being a chapter behind now.
I was
But if you can't
I
get
think
it might be an issue.
I think you've also mentioned chapter 3. No, lab 3. Sorry, because I thought it with
There was an issue where one student mentioned, and a couple of students emailed me, saying that Logger Pro and that software that I gave you guys an addendum to download, all of a sudden is not allowing them to download anymore. So that means they can't get that done. So I'm going to have to look into that. And as a bare minimum, you're getting at least 7 days extension on it, but I might even give you more. It all depends on what I'm going to find out. Like I said, at the end of last semester, it was still working, so I was hoping it would still be now. But obviously, there's something went wrong, so I got to go track down what we can do, talk to our vendors, see about getting another access code or whatever. So hopefully that works out. But remember that test is on hold until then, or that lab is on hold until I get back with you. So you at least have another 7 days to do that. Anybody else? Go ahead, Adrian. You have another question?
Yeah, I have way too many questions because again, I am like so far behind. I'm trying to do the practice tests, but I keep seemingly not understanding the dimensional analysis, the percent uncertainty, and basically the I think it was the graphs for chapter 2.
Mm-hmm.
and basically any chapter 2 problem that involved describing two objects. Because I didn't understand anything about the.
Like the relative velocity stuff, like the water moving with a boat and that sort of stuff, or
Is that the one where it involves two objects to each other?
uh,
Relative velocity?
there was one where you're asked to try to get directly across the stream, or in one case you're trying to find the path of least time or something like that. Uh,
One of them I got for the practice test was about the runners.
okay.
Basically, how much time it took for the two runners to meet up,
Oh,
and I
gotcha.
didn't understand a single thing.
Yeah, so with those problems, those are normally like with two runners, it's a matter of figuring out what the two runners have in common. So are they both running the same distance? Are they both running at the exact same speed? Are they both running for the exact same amount of time? Once you figure out exactly which one of those is true, then it's just a matter of setting those two things equal to each other using the kinematic equations to find expressions for them. So, for instance, if if you say two runners take off, the first runner takes off, and then 1 second later, a second runner takes off, and they give you the acceleration, initial velocity, blah, blah, blah. And they say, after how long will the two runners finally meet up? In that case, those two runners are traveling the same distance. So if you take your distance using a constant velocity idea, assuming that you're not taking into account that they're accelerating it off, you just assume that they're running at constant rate, then you can say, okay, well, their distances are equal. And from velocity equals distance divided by time, you know that distance is equal to velocity times time. So you can say the velocity times the first person's time is equal to the velocity times the second person's time. And the second, one time will be t, and the other time will be t minus 1 second. Say if you started 1 second late, that's the way you go about solving such a problem. If it had the acceleration, then you're gonna have to use the more robust version of the distance equation instead of using distance is equal to velocity times time. Now you have acceleration, so you have to use x. The distance is equal to 1/2 at squared plus v0t plus x zero if possible, but probably not.
I think the only thing I even noticed was the same distance. That's only after from 25 to somewhere. Yeah, 25 meters would technically be the initial for both of them.
The distance that they're traveling total would be 25 meters. Your volume's going in and out for some reason, so I can't hear.
Sorry, it's just I have to bring it physically close. Because the only thing I noticed was that after 25 meters, that's when rudder B starts, and that's technically the range where we need to figure out from 25 meters initial to somewhere.
In that case, you're going to call one distance, x, and the other distance x plus 25 or x minus 25.
Oh my God. X plus 25.
Yeah, remember that's a way to skip adding a second variable and therefore a second equation, all that stuff is you can use tricks like if the total time is 20 minutes and you can call one time t and the other time 20 minus t. Same thing with distances. So you got to remember a lot of those little tricks that you learned in high school algebra 1, high school algebra 2. We in the physics world, at least when you're taking a class, they assume that you were the perfect high school student that went through physics and chemistry, knows about sig figs, perfectly understands every trig, pre-calculus, and calculus thing that you learned in Calc 1 for this course, and that you understood it perfectly. So,
the first step I thought was
mm-hmm.
Because I swore that if they said the speed, that you can't translate that into velocity.
Gotcha.
They said 3 meters per second.
Right.
I don't think you could say that's velocity.
That is technically enough to say it's a velocity, but if they say that it covers 3 meters in a second, like say in the first second, and then something different in the second second, accelerating.
Okay, if it says like over a specific time period, that's speed.
Yeah, you at least know that the
If
average speed is 3 meters per second.
Oh my God, I could have just used that. Like,
Yeah, and remember, average
oh God.
has that double meaning. You can do the distance divided by time, or you can take v1 plus v2 and divide it by 2, as long as the acceleration is constant.
The other one I have a serious problem was the one question I did not do in the homework. It was a thrown ball question, but you're only given the time and nothing else.
You throw a ball upward or something?
You throw a ball upward, it's in for 3 seconds.
It's in the air
And
for
then-
3 seconds?
Yeah, that's what I was given. I just couldn't figure it out from there.
I tell you what,
After-
if you want to take a picture of that and text it to me, I'll work it out and give you an idea, give you a hint, and then if you still don't get it, I can go ahead and give you the full solution.
Okay, yeah, it's just a lot of problems I just don't understand.
That's perfectly normal. The way we treat it in physics is all problems are impossible to solve until you solve them, and then they become trivial. It's just the end.
Oh my God, I didn't read. I was almost about to ask about percent uncertainty, but I didn't read the answer right.
Remember, percent uncertainty is always the uncertainty that you have divided by the quantity itself. And if they don't give you an uncertainty, it has to be at least 1 in the last decimal place. So if they said, what's the percent uncertainty of 5.39? Well, you're going to say, okay, well, the uncertainty must be at least 0.01. So you do 0.01 divided by 5.39. That gives you the decimal. Move the decimal 2 places to the right. That'll give you the percent.
Oh my God, I don't understand this one in that case because it said what is the percent uncertainty in the area of a oh.
So
Wait,
in
what?
that case, you're using
The percent uncertainty in the
area.
area of a circle whose radius is something.
Yeah.
I assumed 5.6 because you had to do the measurement. But that's 5.6 is not right.
Hold on a second. Let me do this real quick. I'm going to share my screen with you.
Yeah, it's just problems like that, and I just get too stressed to be able to read.
I feel you, man. Been there before. Hopefully it should come up on here pretty soon. Okay. So the area for a for a circle is equal to pi r squared, right? And they want to know what the uncertainty in the area is, if the uncertainty in the radius is a certain thing. Is that right?
Yeah, I was looking for the percent uncertainty of the radius. 1.8 times 10 to the fourth. Yeah,
Okay.
1.8 to the fourth power.
So what we know is if you have y equals f of x, then sigma y, the uncertainty in y, is the absolute value of the derivative of f with respect to x times the uncertainty in x, sigma x. So
Oh my
if
God, it's
you want to know the uncertainty in the area, you're going to take the absolute value of dA. Well, let's leave that A off completely. I'm just going to put it next to it. That's d by dr of, now the formula for A is pi r squared.
2 pi r, so 2 pi r.
Exactly. So you get 2 pi r times the uncertainty in r. So did they tell you the uncertainty in the area, or did they ask you to find the uncertainty in the area given the uncertainty in the r, or vice versa?
I think it's basically implied to find the area because they only give you the radius.
So they gave you the radius. What was the radius?
1.8 times 10 to the fourth. 18,000 basically.
Times 10 to the fourth, and that's meters?
Yes.
Okay. So
Yes.
that
No,
means
centimeters. Sorry, centimeters.
centimeters. Okay. So that
Yeah.
means the uncertainty in R is 0.1 times 10.
Okay. Yeah. Not the uncertainty. Right. That was the last sig fig, basically.
Right. You just put
Oh.
in the last spot.
Oh. You have to copy the. Oh. I think that's the part I forgot. One of them, at least.
Mm-hmm.
Yeah, you have to copy the exponent. Okay. Okay.
What other numbers did it give you, or is it just asking you what the uncertainty in the area
It's just only asking for the uncertainty, the percent uncertainty
of what? Of the area or of the radius?
of the area of the circle.
So,
What
gotcha.
is the percent uncertainty in the area of a circle whose radius is 18,000 centimeters?
Gotcha. So,
That is literally the question. Yeah.
159 times R, that would be 1.8 times 10 to the fourth times 0.1 times 10 to the fourth. So sigma, oops. That's 10 to 1, 2, 3, 4, 5, 6, 7, 8. So I would say that is the sigma A. The fractional uncertainty would be sigma A over A. And the A, of course, we got to calculate. So A would be 3.14159. I always do way more sig figs than necessary on this. But times 1.8 times 10 to the fourth. That's centimeters again. And that's squared. So this quantity should be equal to 3.14159 times 1.8 times 10 to the fourth squared. That gives me 1.018 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9 times 10 to the ninth centimeters squared. So sigma A over A is supposed to be 1.131 times 10 to the 8th square centimeters over 1.018 times 10 to the ninth centimeters squared. So I'm going to take 13097.240. I'm going to divide that by 10178.75160. Boy, this gives me 0.1111. That means the percent uncertainty would be about 11.1%. And I don't know what kind of answer they gave you, but this is a way to do it. This way is the propagation of error way, which you can sort of always think about. We're going to be doing a lab on that, propagation of error. I don't think I've given you that one yet, but that will be coming really soon. And when we do that, you'll get better explanation of why that dA formula, that sigma y equals the absolute value of the derivative of f with respect to x times sigma x. you'll have a better sense of why that's the case. What you could do, though, you could also just try calculating the area and then try calculating the area using the radius not as it is, but adding its uncertainty, which would be zero point 0.1 times 10 to the fourth, adding that to the radius, and then calculating the area with that. Then do the same thing by assuming the radius is zero point 0.1 times 10 to the fourth less than the actual radius. And then you have a upper limit of the max of the area and a lower limit of the max of the smallest of the area. You can take that big number minus that small number, and that'll give you the distance between them. Divide that by 2, and that's another estimate of the uncertainty in the area. That's another way of doing it. I'm not sure exactly what they're wanting you to, or which way they're wanting you to do it, but all of these are options. I would say they're probably going to say it's on the order of 10% because they did use 2 digits, so maybe they'll call it 11%, but they might not.
10%. Okay, yeah. That's the closest one. Yeah, I thought I almost said 1.1 because that looked a little strange, but okay, yeah. 10% would be the answer in that case.
Yeah.
Oh my God. Yeah, I'm just having so much trouble with that and dimensional analysis.
Yeah, just remember with dimensional analysis, a lot of times it's just about checking whether the units on the left equal the units on the right, and you're golden. Okay, that's all you got to do is just check the units.
It was it's so strange for me in this case because I'm trying to figure out. Oh, I have to figure out what leads to just
like
because
like
because if you use the units, dimensional analysis replaces the variables with the units they are derived with.
Right. In unit analysis, it's just the units. In dimensional analysis, we replace the kilogram with a capital M. We replace the meter with a capital L, and we replace time with a capital T.
Oh my God.
That's
So
the only
so
difference.
it's basically trying to figure out what combination leads to just the units that you need.
Exactly. So, if you're trying to hypothesize the form of an equation, they'll tell you, it depends on these 3 variables, X, Y, and Z. So you're going to say, all right, I'm going to put X to the A power. I'm going to multiply that by Y to the B power, and then I'm going to multiply that by Z to the C power. And from the description of the problem exactly what units or dimensions the X, the Y, and the Z have. So you can work out what that would be, X to the A, Y to the B, Z to the C. And then on the right-hand side, you want the unit that they told you you're trying to find a formula for. So you put that unit or that dimension on the right-hand side and just work it out and figure out what A, B, and C are. That's the complicated way of doing dimensional analysis, or that's the complicated problems that I could ask you using dimensional analysis.
Oh my God. L. Okay, I think I got it. L divided by G. Because yeah, it was a pendulum. It was a pendulum problem.
Yeah, L divided by G. They probably ask you whether it'd be you could just say L to the Q power times G to the P power. And if they're asking you for a period, you're going to say that's equal to T to the 1 power for dimensions. Or if you said it was dimensional or being unit analysis, then you'd set that equal to seconds to the 1 power.
Okay.
Does that make sense?
Yeah.
I mean, I can write it down if you want, since I do have the iPad connected still.
Yeah, it's probably just going to be ifed me because the online test is no need for lockdown, right?
Yeah, what exactly? The online test is no lockdown. You get to use open notes, open books, Google searches. You're not supposed to look for something someone might have seen the test and then created, but other than that, you can pretty much look anywhere.
Okay, in those.
Yeah.
Okay.
Hopefully you're doing that in a minimal amount of time. My advice is if you're not able to do it without having to look up more than one problem every online test, then you're probably not learning the material as much as you're just getting really fast at looking it up.
That the O01B, the asynchronous, can ask for face to face, right?
Yeah, it's actually all of y'all can.
Okay, thank. I would probably rather do the face to face in person.
Yeah, the only problem is, like I said, if you wanted to take my face-to-face exam, you'd have to show up tomorrow at 12:35. I might be able to do something with
Wait, tomorrow? Literally tomorrow.
yeah, literally tomorrow. That's why you wouldn't want to do that with me. But
Oh no.
I might be able to do something for you Monday if you really wanted to, because I do have a lab Monday, and it's not overly full, so often there's plenty of room as long as you could do it in a not ideal environment. If you're easily distracted, it might not be good for you.
I'll try, but I'll try Monday. I'll send out an email. But
Just send me an email to remind me. But yeah, I'll be glad to do it for you that way. And that's for anybody else too, of course.
the time, yeah, you're just probably gonna give me the time on the email, or no?
It'd just be 12, like I said, it's 12. You can show up a little earlier if you want, but it's 12:45 is what time it would start.
12:45, 12:40, basically noon.
Hmm.
Okay.
If you wanted to, I mean, I could probably figure out a way for you to do it starting at 9 in the morning if you wanted, but I don't know that you'd prefer that. Or excuse me.
That's fine. I think I can do 12:45.
Okay.
Yeah, yeah.
All right. Well, I
I'll
guess I'll
try.
go ahead and let you go then. My knees are aching. I spent my birthday working in the yard, which is something I love, but now my knees are killing me, so I should probably.
I apologize for taking so much. I am just struggling with this.
You're fine, but do send me a photograph of problems that you have difficulty with, including
Mhm.
the answers if it's multiple choice, and I'll be glad to help you out. Not only that, start working on the practice test. Uh,
Yeah, I'm already doing the practice test. It's yeah, I've been saying some of the problems that have been giving me problems.
I'll try. I didn't want to make a separate practice test just geared for this coming test, but I think I might do it, and I'll let y'all know if I do, and that'll give you a little bit more help.
Okay, thank you.
All right. Have a good one, Adrian. And I guess he's out.